It's okay. It's okay. Okay. Well, I think we're all in now. Well, welcome everybody. We've got 65 people. We're considering we'll probably get some more before we start properly. That is, that's extremely good. In fact, one of our best audiences for a long time. We have Catherine Walsh, who's Associate Professor at the University of Leeds in the astrochemistry, I might add. And Catherine, could you tell us a bit about yourself while some more people pile in?
Yes, no problem at all. My pleasure. I'm very happy to be here today to give you a little bit of a historical perspective on the area that I work in, which is in astrochemistry. So a little bit about me. So I did my undergraduate actually in applied maths and physics at Queen's University in Belfast. So you might hear the accent. I am from Northern Ireland originally. And I stayed on there to do a PhD with Professor Tom Miller, who had just recently joined Queen's from UMIST in Manchester. And he actually brought astrochemistry back to Queen's, actually. So Queen's had been quite maybe it's a different talk than what I'm going to talk about today, but a lot of molecular physics had been started at Queen's Belfast. And I stayed on to do a PhD there, and then I stayed to do a few years of postdoc, mainly working on the chemistry of protoplanetary disks, which are disks of dust and gas that encircle young stars within which planetary systems form. And then I moved to Leiden Observatory in the Netherlands for a few years, where I worked in the group of Evine van Dissche, who's a really big professor in astrochemistry as well. So I've been very privileged to work with a lot of very well-known people in this field. And then in 2016, I came to Leeds as what was called then a university academic fellow, and I've been a permanent member of staff in Leeds since. So at the moment, I'm an associate professor, which means that I just do research, but I also teach and lecture and mentor students as well. And I hold a grant as part of the UKRI Future Leaders Fellowship, which is looking at how to seed habitable worlds in planets that are forming around young stars. So if it's okay, I can get started with the talk, if that's okay.
Yeah. Yes, indeed. I think we're pretty well ready to go. We've got 75 people, which is excellent.
Brilliant.
Will you talk to us about 80 years of astrochemistry?
Yeah, brilliant. So I was very happy to agree to give this talk because, even for my own interest as well, to give a little bit of a historical perspective to the field of astrochemistry. So it's quite a big field these days. It's often considered to be quite a new field of astrophysics, but of course astrophysics has been going on for many, many millennia in some form of another. Astrochemistry really started in the previous century. So I'll tell you a little bit about, just a little bit of a background about what astrochemistry is, who it involves, what type of research is done there, and then I'll talk you through kind of the birth of the field, which was really when the first detections of molecules in space were made. So I think it's useful to kind of go back right to the basics of because if we think about galaxies, so galaxies are massive assemblies of stars, dust and gas, which have their own what we call galactic chemical evolution. And that chemical evolution is very much driven by this cycle that you see on the slide in front of you. So stars are born within the gas and dusty clouds that are within galaxies. And when these stars are born, they obviously undergo fusion, and that then creates, over time, converts basically light elements like hydrogen and helium into heavy elements like carbon, nitrogen, oxygen, even all the way up to very heavy elements like iron. And the very first stars in the universe would have been made just from clouds of hydrogen and helium, because that was all that was really available after the Big Bang, as we call it, which would have been the birth of the universe. So this cycle of kind of star birth and star death that has happened over the age of the universe has gradually over time enriched our universe and our galaxy with heavier and heavier elements, and elements that really we need kind of for us to exist, and also for planets even to form. So this is a really nice version of the periodic table, which shows you where kind of the origins of elements in the universe. So anything that's colored green was formed in the Big Bang fusion. That's mainly hydrogen, helium, and a little bit of lithium, so the very light elements. Then the other colors are related to stellar evolution. So yellow is dying low mass stars. So our sun is a low mass star. It will eventually run out of fuel and die. Those are the types of stars we're talking about. In orange, you have exploding massive stars. And you can see here that they're quite important for elements that we need, such as carbon, nitrogen, oxygen, and phosphorus. We have purple cosmic ray fission, which again is mainly light elements. And then you have the very, very, explosive events that happen in the universe, such as merging neutron stars, which create these very heavy metals effectively. And you also have exploding white dwarfs in blue as well. And on the right-hand side, you see kind of the distribution of elements from all these different origins that actually make up life, or humans, as we're part of life as well. So 1% by mass of us comes from exploding white dwarfs, 9.5% comes from the light elements forged in Big Bang fusion, 16.5% come from dying low mass stars, just like the sun. But the majority, 73%, come from exploding massive stars. So those stars that eventually go supernova, creating those beautiful nebula, but also creating those heavy elements that life needs, such as oxygen and phosphorus, for example. So really the only reason we are here today is because these cycles of star birth and star death have enriched our universe with these heavy elements. So that's all about the elements that we have, but I'm here to talk about astrochemistry, and astrochemistry is really to do with molecules. And there's this really nice quote back in 1926 by Sir Arthur Eddington when he delivered his Becquerian lecture at that time. So what he had pointed out at this time was it is difficult to admit the existence of molecules in interstellar space because when once a molecule becomes dissociated, there seems no chance of the atoms joining up again. And at that time, they had, we were kind of starting to learn a lot about interstellar space. So interstellar space is the space between the stars, effectively, which, if you look up at the night sky, looks seemingly empty. But of course, we know now, because we have multi-wavelength observations, that space is not empty and is actually full of clouds of dust and gas, which is what makes up that space in between the stars in galaxies. And what Arthur Eddington was pointing out at that time was that space is a very diffuse environment. So it's very, very low density. And in order for a reaction to happen, to make a molecule, you need things to meet. So you need collisions to happen. So even just doing very simple back of the envelope calculations, we could work out that if space is so empty and is practically a vacuum, then there's no way for things to meet, to undergo a reaction to then form molecules. But within about 20 years, this was kind of proven a bit wrong and what we know actually, a huge amount of space and environments are actually molecular in nature and not just made out of atoms or ions. So a lot of the interstellar medium is made up of what we call these diffuse clouds of dust and gas, which is very low density, quite high temperature, and irradiated by nearby stars. So you have UV radiation. And even in these diffuse clouds, we can actually have quite an efficient gas phase chemistry that can make quite small, simple molecules, so simple diatomic molecules, like small hydrides, for example. And then within these diffuse clouds, there's much more dense regions. And if you have a higher density, you have a higher collision rate. And you also shield yourself effectively from sources of radiation, which means these clouds can cool down to actually quite low temperatures, so of the order of only 10 degrees above absolute zero. And it's within these clouds that we really start to see much more chemistry happening and much more larger, heavier, complex molecules forming. But the fact that these clouds are molecular is what allows them to cool to quite low temperatures, so only 10 Kelvin or so. And what that does is allows parts of those or clumps of that cloud to cool effectively. The thermal pressure, which is supporting the cloud from inside, is no longer able to support collapse against gravity. So gravity wins because thermal pressure support has decreased. And that effectively is how we form stars, just the simple balance between gravity and thermal pressure. If gravity wins, these clumps within the interstellar medium can basically undergo runaway collapse to form eventually a star. And these molecular clouds are molecular in nature. They have quite a rich chemistry. And then we end up in this phase here where we have a central star that is now surrounded by a disk of dust and gas. This is what we call a protoplanetary disk. And this environment is also molecular in nature. So it's mainly made out of molecules because it's cold and it's dense, and it can shield itself from dissociating radiation from the central star. And these protoplanetary disks are also very important because this is exactly where planetary systems form. So you have dust grains within the disk start to stick together, form planetesimals that themselves collide and eventually grow up into form planets. And if you think about our solar system, the reason that our solar system is sitting in a plane orbiting the sun is exactly because our planets formed in a disk around the young sun not so long after it formed. And the next kind of molecular environment that's important for us is, of course, planetary atmosphere. So our atmosphere is molecular nitrogen, molecular oxygen. Gas giants like Jupiter and Saturn are made out mainly of molecular hydrogen. So planetary atmospheres are also molecular environments. So a lot of these different phases in this kind of cycle of kind of star birth and star death, if you like, really involve molecular environments, and those molecules are formed by chemistry that's happening within them. And this is where the field of astrochemistry comes from, because what we want to do is we really want to understand how these molecules form, how they're also destroyed in these different environments, and how we can use observations of those molecules to learn something about their environment as well. And it's a really interdisciplinary field. So we have a huge input, obviously, from physical chemists, from physical chemistry. We have astrophysics as well, so kind of using observations from different telescopes to learn something about the environments that we're looking at. And there's a huge amount of work also done on the spectroscopy and instrumentation side. So the spectroscopy really tells us at what frequencies of light we need to look at in order to uniquely detect these species in space. And we cannot do that without having very specialized instrumentation on our telescopes that allow us to tune at very high spectral resolution, high resolution, to really zone in and tune into those frequencies to uniquely detect those molecules. So it's a really highly interdisciplinary field. So it really brings together people working on observations. That would be one of the hats that I would wear. People working on computational modeling. That could be, there may be simulating the chemistry or physics of the environment. And those models require fundamental data that really comes from laboratory experiments. So these are things like spectral frequencies at which we need to look at to uniquely detect molecules, but also things like reaction rates and understanding of mechanisms that are happening in space rather than under the conditions that we have here on Earth. And then, of course, that spectroscopy also feeds into motivating the building and development of telescopes that then allow us to go and look for those species in space. So I find it a really nice environment to work in because I get to talk to a lot of different scientists with a lot of different expertise, not only just fellow astrophysicists, but a lot of people working on instrumentation and engineering, and also a lot of people working on laboratory experiments as well. So in terms of, so I showed you one version of the periodic table showing you the origin of the element. So this is what we kind of jokingly call the astronomer's periodic table, because not every element that we create through stellar evolution will take part in chemical reactions and form molecules in the environments that we're talking about. So this is another version of the periodic table where the size of the square gives you an indication of the abundance of that element with respect to the others. So you can see here that hydrogen is by far the most abundant element that we have. Then we have about 10% of helium. And then we have, I think it's a few tenths of a percent of other elements like carbon, nitrogen, oxygen, sulfur, neon, argon, some of the inert gases, but also some metals such as sodium, magnesium, calcium, iron, nickel, aluminium, and silicon. And phosphorus should be on here as well, because we're starting to see phosphorus molecules too. So these are the kind of the key elements that actually do take part in chemical reactions to form molecules. So it's quite a small feedstock of material that we have to work with. So the other thing that I wanted to point out is just maybe a little reminder of like exactly how we detect molecules in space. So if we have say a very simple diatomic molecule that's, say carbon monoxide is a famous one, then that molecule will have several different mechanisms by which it can be excited and then emit light. And the mechanism that you might be most familiar with are electronic transitions. So you have electrons that jump within energy levels in the molecule, and then when they jump back down, they emit light, usually at UV visible wavelength. So exactly kind of the peak of the wavelengths of where our sun emits. But what makes molecules unique from atoms is that they are also joined together with a molecular bond, and that molecular bond actually gives many more energy levels that that molecule has access to. So you can vibrationally excite the molecule, so you can think about the molecule being on a spring, as you might be familiar with. You can also twist and torsion the molecule as well, and that's what we call vibrational transitions. They're mainly at infrared wavelengths, so if we build infrared telescopes with high enough spectral resolution, we can detect molecules via the vibrational transitions. And then within each individual vibrational level, we also have rotational transitions as well. And this is to do with the fact that if you have a molecule that has a non-zero dipole moment, as it's tumbling in space and moving, it has moments of inertia, and that changes its rotational state. And just like for electronic transitions and vibrational transitions, those rotational transitions are discretized, so it's like a ladder effectively. So as a molecule jumps from one rotational transition state to another, it can emit light as well. And that's mainly what's written here is microwave frequencies, but what we would call millimeter or submillimeter wavelengths. And most of the environments that I spoke about previously are actually quite cold environments. So the only energy levels you're actually exciting under those quite cold temperatures are these rotational transitions. So we cannot necessarily always see the electronic transitions because they need a lot of energy, high temperature to be excited. Vibrational transitions are the same, maybe around a few 100 degrees, something like that, you would excite vibrational transitions. But if you want to see molecules in cold, dense clouds that are at 10 Kelvin, it's really only these rotational transitions that are populated. And then when they drop down, then we can detect those transitions at millimeter or submillimeter wavelengths. So the other thing that we have to factor in is also where our atmosphere, I suppose, lets us see radiation coming from space. This is quite a nice schematic that shows the electromagnetic spectrum here on the bottom. So we're going from the radio wavelengths on the left-hand side, so wavelengths of order, tens of meters, to the ultraviolet on the right-hand side, where we're talking about wavelengths of tens of nanometers or hundreds of nanometers, for example. And what you see in kind of the shaded regions are the regions of the electromagnetic spectrum where our atmosphere basically shields us from any radiation from space getting through. So we have high opacity down here at very, very long wavelengths, but we do have a window here at radio waves. So something is emitting radio waves, I can get all the way through to the surface. Then as we decrease our wavelengths or increase our energy of our radiation, we start to see those the opacity increasing. So it's harder and harder for radiation to get through the atmosphere. And this is because of water in the atmosphere. Water is actually a really effective absorber of radiation, especially at these millimeter, submillimeter wavelengths. And then we have a region here, which is around far infrared wavelengths, which is makes our atmosphere also opaque again. And that's just because we are radiating at these wavelengths as well. So it's very, very hard to see faint emission from space over the background emission that we are emitting naturally. Then as we go towards the infrared, which is a few microns, so a few times 10 to the minus 6 meters, we start to open up the optical window. And then here you can see the visible light window as well, which is at a few hundred nanometers, 400 to 600 nanometers or so. So there's only a few windows of the electromagnetic spectrum where we can actually do astronomy from the ground. So for example, here we have the GBT, which I'll talk about a little bit, which operates at radio waves. We can do that at 0 altitude, at sea level, that's no problem. We have telescopes like ALMA, the Atacama Large Millimeter Array, that operates here at millimeter wavelengths. And we put ALMA in the driest place on Earth, apart from Antarctica, which is the Atacama Desert, to get above, and that's at altitude, about 5 kilometers altitude. So that's to get above as much of the atmosphere as we can, but also in a very dry atmosphere because water is a very efficient absorber of light. In Europe, we have NOEMA, which is an array that's in Spain. And again, that's at altitude as well. And for this far infrared kind of region where the atmosphere is really opaque, we have to go to space. And the last big far infrared mission that we had was Herschel, that actually did a huge amount of work in this wavelength range here. Then we have the visible light telescope. So these are the telescopes like the VLT, for example, which is the big ESO telescope again in Chile. In America, we have the Keck telescope, and they can be done from the ground, but again at altitude to get above as much of the Earth's atmosphere as possible. And then if you've been paying attention to the news, you might know about JWST. It's the next kind of big mid-infrared to near-infrared mission. And again, to get to mid-infrared wavelengths, we really need to go to space. It's very, very difficult to do mid-infrared astronomy from the ground just because of the atmosphere and the background that we have. So all of these missions that I've talked about, observing facilities that I've talked about, have all been used to detect molecules in space and to understand something about their abundance and their origin. So just a little bit about what we actually, what typical astronomical observations look like. So this is a really nice example from Herschel that I just spoke about, which was the far infrared mission. And this is what we call an unbiased line survey, where we have a high resolution spectrometer. We pointed at an object. In this case, this is the Orion Nebula, which you can see in the background at infrared wavelengths. And we basically scan across in frequency or wavelength, measuring how much light we have in each of those wavelength bins. This is basically creates a very high resolution spectrum of the object that we're looking at. And so these are emission lines, and they're basically emission lines coming from rotational transitions of molecules. So again, Orion is a molecular cloud. It is being irradiated by a massive star called Sigma 1 Orionis, but most of the cloud is actually quite cold and quite dense. So it's only rotational transitions that you're exciting. And you see here that we actually can see some quite large molecules, things like methanol, the simplest alcohol. We have cyanides like hydrogen cyanide. Water pops up everywhere. Water is actually very abundant in space. It's very easy to make that. We have a few other larger things like acrylonitrile, methyl formate, dimethyl ether, if you remember, obviously, your organic chemistry. These are simple versions of esters and ethers and nitriles. And we can see and uniquely identify those molecules from their spectral lines and emission spectra. But it's not the only way that we detect molecules. We can actually also see molecules in absorption as well. And to do this, we need a background source of light, in particular, usually at infrared or millimeter wavelengths. So if this is an interstellar cloud in this little cartoon, if you have a background star that's behind your interstellar cloud, then that light will travel through the cloud and be absorbed by any molecules that are sitting in the cloud. Similarly, if we have an embedded forming star that's still collapsing and warming up its surroundings, then this becomes warm. That creates an infrared background, which then travels along the line of sight here to the observer And again, we can see absorption bands and absorption signatures of molecules along that line of sight as well. And in contrast to the emission spectra, where we're looking at the emission as a function of frequency, in the absorption spectra, we're actually looking for absorption bands superimposed over and above kind of the background. So that's what you're looking at here. We have wavelengths at infrared wavelengths here, and microns are going from about 2 microns to 21 microns roughly. Then this is the flux that we're measuring from our background object. This is quite a famous spectrum now, taken quite a while ago, but by one of the best instruments that we had available at that time, which was ISO, the Infrared Space Observatory. And what you can see here is very strong bands of water. And this is actually water ice, not water gas. So we can actually see ices in space as well. We have here a weak band of methanol. We have a CO2, which has got this very sharp band. We can see the dust grains through their silicate absorption features here at 10 microns and at about 16 microns. And we can see other small molecules like ammonia and carbon dioxide and methane. So we tend to try to use both methods to observe astrophysical objects. Sometimes we can only use emission spectroscopy because we don't have any background sources. But we also, and especially now with JWST, we exploit absorption spectroscopy as well, in particular to look for solid phase molecules as well as gas phase molecules. So now I'm going to shift a little bit because that was a little bit of background on how we see molecules in space and the different environments that we might probe there. So I'm going to kind of give you a little bit of a historical perspective on when astrochemistry basically was kind of born as a field. So this is the year on the x-axis going from 1940 to more or less the present day. So I think this dates up to 2021. And what you're seeing on the y-axis is a cumulative number of detected molecules. So you can see that astrochemistry, as I'm going to show you, started in about 1940. You can see there wasn't much actually happened. We only detected a handful of molecules then, until kind of 1970s or late 1960s, 1970s, when we had kind of the birth of radio astronomy. And since then, it has really kind of just been almost a linear trend with time. So at the moment, we have more than 240 molecules uniquely detected in space. And kind of since 2025, when we had a few new facilities come online, we're averaging about 6 detections a year. And it's a huge effort by the whole field to understand what it is we're looking at and how these molecules form in these different environments. Because as I'll show you, some of them are quite unique and a bit exotic compared to the molecules that we have on our planet. So I've told you about absorption spectra for the reason that the first interstellar molecules were detected via absorption spectra, in particular towards bright stars. And this is a paper from 1938, so nearly 85 years ago, I suppose, yeah, something like that. And these are basically photographic plates. So this is how spectroscopy was done back in the day. And then on the right-hand side, you can see traces of the flux going across these photographic plates. So where you see a gap in the plate corresponds to an absorption band in the spectrum. And you see here, there's a few things highlighted. So for example, these D transitions here correspond to the sodium transitions, the sodium doublet transitions. You can see at the bottom here, you have absorption from potassium, and I think this is hydrogen and helium lines. And you can see again, the potassium line here and the hydrogen helium lines here as well. So there were many of these spectra taken at the time that these techniques were then available and reliable. And I'm showing you the atomic spectra here because that's what people were focused on at the time. They were more interested to know which atoms were there along the line of sight. But actually, when people started to dig into the spectra a little bit more, they realized there were a lot of unidentified lines. So there were lines that could not be attributed to actually atoms who had had their spectra very well characterized even at that time. So it was only by exploration of these unidentified lines were the first molecule securely identified in space, and that was the CH molecule, which is a radical as well. So again, a weird molecule for us. That's at 4,300 angstroms, or 430 nanometers, and the cyanide radical as well, which was at about 3,874 angstroms, or 387 nanometers. And what you're seeing in the background is the telescope that made those detections and did these observations at the time. This is the Mount Wilson Observatory in California, with this image taken around 1924. And this was a real workhorse for astronomy at the time. This was also the telescope used by Hubble, for example, to first measure the Hubble constant. So the paper that reported the first detections of molecules in space actually doesn't have any spectra in it at all. It's quite interesting to go back and look at these papers. And this is a paper by McKellar, a single author paper. And lots of people were going through these absorption spectra along diffuse sight lines towards bright stars and realized that a lot of these lines remained identified. And they identified two in particular. So again, this one at 4,300 angstroms and this other one here at 3,874 angstroms. And they actually started talking, I suppose, or looking at the physical chemistry literature and realized that there was ongoing parallel efforts to characterize the spectra of molecules. So if I can just point out here, so this is a table from that paper looking at the molecules CN, CH, and NaH. And these are the two kind of secure detections that I've just spoken about. So this is the CH molecule at 4,300 angstroms. And if you look here, this was able to be identified because of this report by Jevons at the time on the band spectra of diatomic molecules, which had been published 8 years previously in 1932. So astronomers started to have to talk to physical chemists and look in the physical chemistry literature to start to identify these unidentified lines. And you'll see here as well, this other secure detection at 3,874 angstroms references this work by Jenkins, which again is a paper in Physical Review, which was characterizing the spectra of small diatomic molecules. And again, that was in 1938. So these two things were in concert and going hand in hand. On one hand, you had astronomers scratching their head, wondering what these unidentified lines were. On the other hand, you had the birth of kind of molecular, characterization of molecular spectroscopy, better and better lab techniques allowing nice high resolution spectra to be taken of molecules in the lab. So we have CN, we have CH. This is quickly followed by the CH plus cation. So that's CH with an electron knocked off, so the cation. And this is a nice paper again by Douglas and Hertzberg from 1941, where they actually started what I would call more kind of joint astrochemistry, because they identified that one of the carriers of these lines was likely to be the CH plus molecule. And what they did was they did a lab experiment where they made, as best as they could, the CH plus cation using C6H6 vapor. So that's benzene vapor, which was then dissociated and split into multiple fragments. And then they measured the spectra and they were able to uniquely identify that these three interstellar lines belong to the same molecule, which was CH. So on one hand, they had predicted that this could be the carrier, but on the other hand, they were also able to do the experiment to then uniquely say, yes, these lines are due to this molecule CH plus. So I think that this is one of the first times where we see physical chemistry and astronomy really in concert with each other, which I would say is really where astrochemistry comes from. So that was kind of the early days of astrochemistry, and that was done using optical absorption spectra towards bright stars. And there was a bit of a gap, as if you'll remember from that plot that I showed, where nothing much new was detected until kind of the 1960s. And that was really only possible because at that point was really the advent of radio or submillimeter astronomy, which is really the kind of the workhorse of how we detect molecules in space today. And the reason that we need submillimeter or radio astronomy is because if we look at the interstellar medium, it's not just one thing, it's not just one phase. So this is a nice optical image of the Carina Nebula. So you have Eta Carina down here on the left-hand side. It's a massive star at the end of its life. you see a massive stellar cluster in the center here that's irradiating its environment and probably destroying any molecules in its vicinity. But the interesting thing is, if you look here on the edge, you see these dark regions, and these dark regions are these molecular clouds that I was talking about, these clouds of dust and gas that are dense enough to shield themselves from this radiation from the central cluster. And these clouds of dust and gas are so dense and so cold that they're mainly molecular in nature. So if we want to understand the composition of these clouds and understand also something about the conditions under which stars form, we have to use rotational transitions of molecules, because it's only those transitions that are excited in these dense regions. So if we want to probe where stars form, we want to understand also how planets form around those stars, it's these regions we need to look at, and these regions only really emit light at submillimeter or radio wavelengths. So how do we do that? Well, we exploit many different observatories, of course, spanning that wavelength range. And this is quite a nice summary of the number of molecules detected at the different wavelength ranges that observatories can operate at. So you already see here the 5 molecules detected in the visible and ultraviolet, which is over here in the pink. Then as we go to heavier and heavier molecules, so that's what's on the x-axis here. And this is basically a measurement of the probability of finding a molecule of that mass at that wavelength range. Here we have in green the submillimeter range, so slightly less than a millimeter from a few hundred microns. In orange, we have the millimeter range. We can see that's 137, and the peak of our distribution is getting more and more, is heading towards larger and larger molecules, or heavier and heavier molecules, okay? Because the more massive the molecule, the lower the frequency those molecules will emit light at, and also the longer the wavelength then is needed for detection. So you can see here we've also got quite a few molecules detected even all the way down into the centimeter regime, which is really the true radio regime. Another thing for going to these wavelengths, these longer wavelengths, is not so we can see bigger and bigger things which have their fundamental transitions at longer and longer wavelengths, but also because molecules can only really uniquely be identified once they're sufficiently big, by the rotational spectrum. This is very different to other techniques like in the infrared. And this is because rotational spectra have a unique spectral fingerprint. So here I show a synthesized spectra of formamide, which is NH2CHO, at around 1 millimeter in wavelength, so about 300 gigahertz in frequency. And this is the intensity of the spectrum of formamide in just arbitrary units, just for illustration. And of course, formamide looks something like this. We have an amide group and we have a formyl group. But if we take another molecule that's not so different in mass, shall we say, so this is methylamine, we have a methyl group, but also an amine group as well, then its spectral lines sit at very different frequencies from those of formamide. And that's because what I said at the start, the arrangement of atoms and the nature of the atoms that make up the molecule uniquely identify it. But it's also because of that shape that really distinguishes between molecules. We change the moments of inertia and we change the rotational energy levels, sometimes quite substantially, uniquely tune our spectrometers to pick up light only coming from that species. So it's a way, by going to these longer wavelengths and kind of lower frequencies, it's a way to really start to uniquely identify big molecules. So towards kind of the modern era of astrochemistry, this was really driven by radio astronomy, or submillimeter to radio astronomy. And a huge amount of work in those years was done by the 36-foot telescope on Kitt Peak, Arizona. And that was operational from the late 60s, actually through already to the year 2000. And it was actually upgraded in the 1980s as well. And this single dish telescope was responsible for about 33 out of the 240 molecules detected to date, so about 14% overall. Then we kind of had the Europeans maybe take over for a little while. So this is the IRAM 30-meter telescope, which is on the Pico Valletta in Spain. and it's been operational from 1984 to the present day. So, you know, these facilities can have a really long lifetime if they're obviously well looked after and continue to receive funding as well. And ARAM has really been the workhorse, I think, of astrochemistry. It's actually detected 64 out of the 240 molecules so far, so about 25%. And then you've already met this one before. This is the Green Bank Telescope. This is in West Virginia in the USA. And it's one of the newest facilities that we have. It's been operational since the year 2000. And it's been doing a lot of work very, very recently, actually, because it works at centimeter wavelengths, it allows us to start to see some really, really big things that only really emit light down there. And it's been responsible for about 12% or 28 out of the 240 molecules that we've detected so far. So we do have telescopes like ALMA that are large arrays that act as one big giant telescope, but by far it's single dish telescopes that have a big collecting area and high resolution spectrometers that allow them to really resolve line emission and distinguish line emission. They have been really the workhorses for astrochemistry. Single dish telescopes have really been the ones to advance, I would say, our field. So this is kind of the array of molecules that we've detected to date. And this is the first part of a two-part table. And we're going from simple diatomic molecules, something that you've met before, of course, is CH and CN and CH+. You can see that we also see things like carbon fluoride plus. We see phosphorus molecules like PO or phosphorus monoxide. And generally, as we increase in size or number of atoms, we tend to see that the number of molecules that we detect at that atom size or mass range tends to go down. But there's a huge diversity of molecules that you see here, not just the common ones that we have in our atmosphere, like molecular oxygen or molecular nitrogen. We see a lot of radicals, we see a lot of cations, so you know, things like this, like HCS+. So we find that molecules can protonate a lot. They like to hang on to a proton. We also see anions as well, so negatively charged molecules that like to hang on to an electron. We see cyclic molecules, including 3 carbon members, as well as things like benzene. And we also see organometallic molecules as well, things like, if you look here, this is MgC3N, so magnesium, like a carbon chain with magnesium on one end and nitrogen on the other. But as I've been pushing the point, we can actually now uniquely detect these really big molecules. And actually we're getting up to quite routinely now seeing molecules that have 12 to 13 atoms. And again, there's a huge diversity in the types of species that we see. So we see highly unsaturated carbon chains. So for example, here's HC9N, so a carbon chain with a nitrogen at one end, a hydrogen at the other end, which is not something that would exist naturally under conditions, the pressure and temperature of the Earth, for example. We see these PAHs, these are polyaromatic hydrocarbons. So basically you can think about these like, you know, benzene rings that are kind of stuck together in various different forms. And we also see fullerenes as well, so these carbon cages such as C60 and C70. So we see unsaturated carbon chains, we see organic molecules, so we start to see things like those ethers and esters that we know from organic chemistry. We see branched molecules now as well, as I'll show you, aromatic molecules, and we also see these carbon chains as well. Ask for us to explain just why we have this diversity in molecules we see in space and the chemistry that's kind of controlling their abundance and distribution. That's really, you know, a lot of what astrochemistry is about. So for the next few minutes, I'm going to show you a few examples of, I would say, particularly exotic species that we've detected in space, and maybe species that you might not have, you know, thought could naturally exist. And the first one I wanted to point out was argon H+ and helium H+, because we're taught in school that the inert gases don't take part in chemical reactions, but actually in space that doesn't hold anymore. It's not really true. And argon H+ was actually detected using Herschel, so the Herschel Space Telescope, because these hydrides actually emit most of their light kind of more towards the terahertz regime, which is the far infrared. So we need to go to space to do that. And we see there's 2 lines of argon H+ here, the 1 to 0 line and the 2 to 1 line. And the image that you see in the background here is the Crab Nebula. So this is effectively a star that's at the end of its life. And obviously there's this very interesting chemistry happening in its circumstellar envelope. And then here we have helium H+, and this is probably one of the first molecules that was ever able to be formed in space, because early, after the Big Bang and after Big Bang fusion, we had hydrogen and we had helium. So this is of interest to actually try to see if it exists in our vicinity, because it is probably one of the earliest molecules. And again, this is in a dying star that this has been detected in. And you can see here, this is at, again, far infrared wavelength. So this is of the order of 149 microns. This was interestingly detected using SOFIA, which was a far infrared telescope that was basically in a Boeing 747 that was then flown at high altitude in order to get above again that background radiation. That means that we can't do far infrared astronomy from the ground. So how do we actually make these weird molecules? Well, we basically take an inert gas like argon or helium and we ionize it, creating something that is actually very reactive, right? So if you have photons of sufficient energy, or even X-rays, as you would do around a star that's gone supernova, then you can knock an electron off argon and helium. That creates a reactive ion that then can react with either molecular hydrogen to give you argon H+, or with atomic hydrogen to give you helium H+. This is a reaction called radiative association, where the molecule stabilizes by emitting a photon. And a lot of molecules actually form via these types of reactions. So the next kind of weird class of molecules, which is something I've also spent some of my career looking at as well, are these carbon chain anions. So these are long unsaturated carbon chains that also seem to like to hold on to an electron, making them negatively charged. And this particular detection here is of carbon 8H-. So you have 8 carbons in a row, a hydrogen at one end, and then the electron seems to like to sit over here on the other carbon end. And we think that these species can form in space because these long unsaturated carbon chains, well, there's a lot of carbon that's floating around and we get quite efficient carbon insertion reactions. So, and they don't get saturated, so hydrogens can add on because the reactions to do that step are just slower than the reactions to add carbons or carbon radicals. So we tend to see that these long unsaturated carbon chains can grow quite efficiently with gas phase chemistry, just in these molecular clouds. And then because it's a long linear molecule, they also have quite a large dipole moment, which means that they can actually hold on to an electron as well. And then you see here on the right-hand side, the detections of this molecule in space. And you can see this is at different wavelengths to what I talked about before. This is at 44 gigahertz. So this is really at centimeter wavelengths. And you see here we have 1, 2, 3, 4, 5 lines that have been detected of this molecule in space. So again, a very unique type of species that we wouldn't necessarily see here on Earth. So we're also starting to see some of these larger organic molecules as well. So this was the first branched organic molecule detected in space. So this is propylcyanide. Where we have the 2 different isomer forms. So the unbranched version, N-propylcyanide, and the branched version here with the methyl group placed on the central carbon, the I-propylcyanide. And in this region here called Sagittarius B2, and you might know Sagittarius A star because that's the center of our galaxy. And the color map that you see in the background here is kind of the continuum, like the image of just emission coming from the center of our galaxy. And Sagittarius B2 seems to be a very active, chemically active kind of large molecular cloud within which we think stars are forming, and in particular massive stars are forming. So a lot of molecules that we detect in space are actually detected for the first time towards this massive star forming region, Sagittarius B2, which is actually very close to the center of the Milky Way. And here again, just as an example, you can see in the orange, these are the detected lines of these different species. And you can see how difficult this can start to be, because in green, what we have are lines from other species. So you start to see that for a very chemically rich environment, it can sometimes start to be difficult to disentangle emission from individual species, just because you have so many lines that you start to get what we call blending and kind of overlapping of lines. So you have to look for parts in the spectrum which don't suffer from that blending. And you can see here a nice example of how they were able to do that for these two species. And then we kind of come on to things that are maybe a little bit more life related, I suppose, because we've now detected actually the first chiral molecule in space. And chirality is an interesting phenomenon for molecules. This is like some molecules will have a left-handed and a right-handed version. So basically, yeah, it's kind of two chiral, isomers, if you like. And this is the first detection of R-propylene oxide and S-propylene oxide. And whilst we can't see the chirality, whether or not these molecules are left-handed or right-handed, it does show that these types of molecules are synthesized in space and are sitting in these molecular clouds. And the reason this is interesting is because we seem to have evolved on Earth to preferentially use left-handed molecules for whatever reason that might be. And it's a interesting kind of line of research to see if some of this chirality might be actually set before, chemistry on Earth has happened. And again, this detection was enabled by a centimeter wavelengths, and it was done in absorption. So they were able to see 3 absorption lines uniquely kind of attributed to this chiral molecule. And again, this is Sagittarius B2. So this is this very chemically rich environment that we have in the galactic center. And just to finish off this little bit, there's been an ongoing mystery since those very, very first spectra taken, when we were able to do that towards bright stars. We've had these mysterious absorption bands, which we call the diffuse interstellar bands, or DIBS for short. And you see here an example of some of those on the top, and you see also an example on the bottom as well. And this has been, again, an area of astrochemistry that's been very active since we found these diffuse interstellar bands that could not be attributed to a single carrier, neither atomic nor molecular in nature. And it's only really been in the past few years, this is back a few years ago in 2015, that we started to realize that some of these could be attributed to these fullerenes, so these carbon cages. And in this work led by Campbell and collaborators, they were able to show that at least 2 of the observed diffuse interstellar bands were due to carbon 60 plus. So carbon 60, fullerene, which has been ionized, it's had an electron knocked off of it. So we're starting to realize that it might be these big macromolecular structures that actually may be floating around in space. How they form, we're still not sure, but they could be now responsible for some of those observed diffuse interstellar bands that have been an ongoing mystery for 80 years since really the birth of astrochemistry. And then just to finish, I think it's interesting to talk about astrochemistry in situ as well, because everything I've talked about so far is remote sensing. So we have a telescope, we collect light, we take a spectrum, we analyze the spectrum. But we can actually do astrochemistry in situ as well, mainly in the solar system, of course, because that's the bit of space we can get to. And Titan is a very interesting object. It's a moon of Saturn, and it's the only other object, aside from Venus and the Earth and Mars to some extent, that has a thick atmosphere. So most of the other moons of Jupiter, Saturn, they're icy rocks, basically. They don't have a thick atmosphere, but Titan does, and it's mainly molecular nitrogen, just like the Earth, with about 5% of methane. And actually, even just that 5% of methane, Titan's atmosphere has a huge amount of chemistry ongoing into it. And what you see in the background here is the Huygens probe. So this was launched from the Cassini mission, which visited Saturn back, God, it would have been like 1990s. And the Huygens probe was basically dropped, and it had a mass spectrometer on board, which is another way of saying measuring composition, where you take a molecule, you ionize it, you pass the ions through a magnet, basically, and then that spreads out the fragments by mass. So the higher the mass, the lower the deflection. So you can use mass spectrometry, basically, to also do astrochemistry in situ. And from the Huygens probe, we could see that actually Titan's atmosphere was very chemically rich. So not only did we have nitrogen and methane, you can also see things like CO2, you can see things like ethane, C2H6, and in fact, things even as complex as benzene, C6H6. So through mass spectrometry, you can also do astrochemistry as well. And then another really good example of this is the Rosetta mission, which visited Comet 67P, images of which you can see here. And this was an ESA mission, which for the first time flew an orbiter to orbit a comet, and it orbited it for about 2 years of the mission duration. And for the first time, we could see really what these objects looked like. So comets are basically leftovers from the formation of planets in the solar system. We used to think they were like icy dust balls or rocky snowballs, something like that. But we could not really have comprehended just the complexity and shape and morphology and composition of these objects. So the Rosetta mission was really the first time that we were able to do that. And Rosetta had actually a machine on board called Rosina, which was a mass spectrometer again. And two really, really interesting results from that mission. First of all was the detection of glycine in the comet. Glycine is the simplest amino acid. So we can make amino acids in space. That's a bit crazy to us, but it seems to be a concrete detection. But also that there's quite a lot of phosphorus in these comets as well. And phosphorus is an important element actually for life. It's one of the 5 key elements that life needs. So really interesting results from this astrochemistry in situ showing us what these comets are made out of. And then you might think, well, why does it matter? Well, one of the theories for how the Earth became actually a water world is that a lot of the water, including all of the other stuff in the comet and asteroids, was delivered by impacts when the Earth was young. So following the formation of the Earth, the surface would have been molten, a lot of volatiles like water would have boiled away to space. And we think that there was a phase of replenishment where comets and asteroids hit the Earth and actually replenished, if you like, those lost volatiles, things like water, but also, as we know now, elements like phosphorus and possibly even simple amino acids like glycine. Okay, so that brings me to the end. So I went on a little bit longer than I anticipated. This is a little summary. So we've now seen more than 240 molecules in space since the 1940s. The species we see are exotic compared with terrestrial molecules. So we know that space has this very unique, but also very rich chemistry. These detections have really been advanced by the advancement of radio astronomy, especially since the late 60s, early 70s, but also in concert with laboratory astrophysics, in particular spectroscopy. And I've also told you that astrochemistry can be done in situ, especially in the solar system, or specifically in the solar system. So we know that large organic molecules can not only be made in space, but also are present in comets, but also planetary moons. And then finally, I think the detection of glycine, which is the simplest amino acid, really shows that the conditions in space are actually favorable for the synthesis and also survival of these, what we might call prebiotic molecules. And I'll finish there. Thank you for listening.
Thank you very much, Catherine, for a wonderful talk, whereby you demonstrate not only the importance of astrochemistry, but the fascination of its history. Now, I have a few questions here, and as it happens, some of these questions also parallel questions I have. So
okay.
We'll take a little while, but we'll get through it. So my first question is really the most simple one, and that is that how do you know that the molecule you're dealing with come from a particular plate, given that, of course, you know, that you've got a lot of space between, say, for example, the Andromeda Nebula and here. So how do you know, for example, that a particular molecule is in Sagittarius star cloud or the Orion Nebula, when in fact it could come from somewhere in between?
So it's a very good question. I think that we have actually quite well mapped the structure of the Milky Way, mainly using the hydrogen 21 centimeter line. So we actually pretty well know where the dense regions of the galaxy are and where the diffuse regions of the galaxy are. And we've mapped that not only in terms of density distribution of gas, but also velocity distribution. So we know the line of sight velocities of a lot of these large star forming regions, for example. So you can use the source velocity to say that if I see a Doppler shift in my line, that could be coming from this cloud or object that we know has that source velocity. But of course, if you're looking through, so you can think about like this is a pencil beam. So you're looking through, a line of sight that might have lots of clouds and objects along the line of sight. But if each of those have a slightly different velocity relative to us, then you see those Doppler shifts. You can separate out actually in velocity space, which is really, really cool if you think about it. And then the other thing is that we actually have a lot of our telescopes have quite a small field of view. So they're big, so they have a large collecting area, but they also have quite a small field of view, which means that we can really zoom in on individual objects. So if we wanted to, for example, look at a particular dense core in a star forming region, we have sufficient pointing accuracy and a small enough field of view to really zoom in on those objects. So we can filter out everything else that's going on and really zoom in on individual objects.
Yes, I've got a similar question that was from somebody else. I have a similar but slightly different question, which your answer may answer as well. And that is within a gas cloud, and you have that picture of a star within a gas cloud or starlight going through a gas cloud. Is there a way of telling where a molecule is in the line of sight? I know in terms of what you might call X and Y, we can say, but there's a little bubble of carbon monoxide here or whatever.
Yeah.
But is there a way of telling where a molecule is in our line of sight within a cloud?
That's more difficult because when you do a line of sight absorption, you're basically doing it's the equivalent of taking a pipe, or like, I can't think of the word, a pipe of gas, a column of gas, a tube of gas. That's the word I was thinking of, a tube of gas. And what you see is a cumulative effect along that line of sight from all the molecules that are in that kind of tube, if you like. So it's more difficult then to ascribe a spatial distribution along the line of sight in absorption spectra. That's a good question. We see the cumulative effect. It's the But when you use emission, you get more information to some extent because you can use velocity shifts to determine if you've got individual clouds or one cloud, and you also get the X and Y factor as you said as well.
Yeah. Now I've got another question from Henry Repser, who says that when you talk about molecules in various environments, are there any molecules which have been detected in the presence of very strong magnetic field, sufficient that is to send their spectroscopy?
So you're talking about
molecules exist in such fields, or can they exist in such fields?
So I'm just looking at the question here. So that's a good question. Magnetic fields in space tend to be quite weak compared to what we even just a magnet you might have on your desk. But there are some regions, so for example, some stars have very, very strong magnetic fields in their vicinity. And there we can see the Zeeman effect, basically. So we can see the splitting of the line due to the Zeeman effect. So a single line basically splits usually into three. It is quite rare because the magnetic fields are quite weak. Because space is vast. So even if you've got something that's a very strong magnetar or something like that, the influence of that magnetic field won't go so far out because of the 1/r² effect. So we can see the Zeeman effect, but we can only see it really in proximity to objects like stars that do have sufficiently strong magnetic fields. And then we can use the splitting to measure the magnetic field strengths as well.
Yes, I've got a similar question, but a different question, which, to be fair to you, probably doesn't fall within your own area. And that is that I once heard a talk by Emma Bunt, who was then the president of the RAS, about water and Jupiter and other chemicals in Jupiter and Ganymede. And the thought occurred to me that you both had strong radio waves from Jupiter. Everybody knows about those. They were one of the first radio waves detected. And also a very strong magnetic field in Jupiter and Ganymede, nowhere else. And I did raise the point to Emma whether one could detect an NMR spectrum or water in such an environment. Now, I've asked various NMR chemists about this, and they will have a sort of poo-hooed the idea. But doing a back of envelope calculation, I reckon you could probably get a spectrum in the radio in the kilohertz region, but I have no idea whether one could detect such a thing or not.
Kilohertz is very low frequency. I don't even, that would be really low frequency. I don't even think our lowest frequency telescopes go that low, actually. Maybe low far, maybe, which is one of the lowest ones. But yeah, it's an interesting question. I think my understanding, because I'm not really, I'm not an expert on magnetic fields. That's, you know, it's like here be dragons for a lot of us are magnetic fields. But I think that the magnetic field,
you've got experts in NMR who are not interested in astronomy, and you get people who are interested in astronomy who know nothing about NMR.
Well, this is it, but I think, I think that the magnetic field strength generally on just normal standard objects on Earth is much stronger than, but it's proximity as well, right? It's how close you are to the dipole that's generating the magnetic field as well. Yeah.
Okay, now I've got another question here. They're all quite technical. Are there any evidence of intermolecular condensation of polyene ions, like the one you mentioned, the HC8?
Intramolecular condensation. I don't know what you mean by that. Do you mean like polymer formation or something like that?
Well, actually, Hendry asked a similar question, which may solidify the question a bit, which say, can the polyene form rings? So can you get circular?
Yes. So this is really interesting, actually, because we looked at this when we were investigating anions, and actually you don't get cyclization until about 10 carbon atoms. So even though you can make carbon rings of like 3, 4, 6 carbon atoms, for these carbon chains they tend not to cyclize, if that's the right word, until they reach like 10 or more carbon atoms, and then they do start to form these large ring structures. And that's mainly been done using computational chemistry techniques to look at the stable structures that you can generate once you get those large carbon chains.
Well, computational chemistry is Hendry's subject, so that's partly why I mentioned it. I was going to say that they're basically polyacetylene, aren't they, effectively?
Yes, you can kind of think about it, but there's only one hydrogen, right? So they're very weird. I mean, you can get things like C4H2, for example, which would be like the simplest polyacetylene, if you like. But these long carbon chains really only have one hydrogen. So it's basically, they're stable because you've got an alternating triplet and singlet bond between the carbons, which seems to keep them happy. Yeah.
Now, my next question is related and maybe a little bit silly, so forgive me. But you mentioned acrylonitrile. Now, one of my interests is the history of synthetic rubber. So I was sort of wondering, if you have butadiene in space, you could, in theory, make a synthetic rubber by combining butadiene with acrylonitrile. I would raise a more general question. Is there any sort of conventional chemical polymerization in space, or are the concentrations of the molecules far too low for that sort of thing?
I think it's a combination of so you need polymerization is an interesting question, I think, because I think you need condensation in the sense of what I would call condensation, which is the phase change between gas and ice. But you don't have liquid in space, right? You can only have liquid on planetary surfaces where the pressure is high enough to have that phase available. So you could do it in the solid form, but then you would need high concentrations in order for polymerization to happen. In the gas phase, I think it would be really hard because it's really gas phase kinetics that's controlling everything. So it's literally collisions between reactants and reaction that's helping to build up these species. So I have a feeling that polymerization would be very difficult, and certainly could we detect things like polymers in space? I think it's really hard because if they're symmetrical and they don't have strong rotational transitions, then we can't see them as well because they just don't emit light. Yeah.
So there was that problem as well. Right.
Yeah. And
Okay,
then,
well, thank you very much, Catherine. A
problem?
lot of people have said what a wonderful talk it is, but I think that is about as far as we go to questions are concerned. And
Brilliant.
indeed, it's now 3:10, so I think we should give everybody a break. I would just like to say that we have broken our record. This is the most attended talk we've had so far, which is particularly impressive since the last one was during the pandemic when we didn't really have much else to do. So congratulations, Catherine, on having our largest audience so far.
Well, I'm very happy about
everybody.
that. I'm very happy about that. Thanks everyone for turning up today. Yeah.
Well, that's right. Thank you indeed, everybody. Just one last comment to the audience at large. Next week, we've got Peter Forshaw talking about the history of alchemy in the medieval Europe, so a very different subject, but I hope we can get a similar sort of audience, perhaps not, for that one. In the meantime, thank you very much, Catherine, for a wonderful talk. Thank you very much, everybody, for coming along, and I hope you all have a nice afternoon. So goodbye for now. Bye.
Cheerio. Bye, everyone.